Hello, everyone, and thank you so much, George, and everyone else for this time. Okay, as you see, I will share the information with you about my work about impacts of different contracts and policy constraints in a distributional robust approach. I will talk about first the introduction, the base of the things that I did in this work, and then periodic contract and single contracts. I will show you the difference of these two contracts and why I wanted to choose or work on single contract. Then I will show you, okay, we can use it for emissions, for like environmental corrective actions. And to have some examples, I've used emissions capacity constraint, emissions corrective tax, and cap and trade system. In cap and trade system, I will incorporate a buyback contract as well to see the influence of that in our model. And then we will see some key results. Okay, the base of my story is actually a Stackelberg game between a manufacturer and a retailer when the manufacturer is the leader of the market, make the decision for the wholesale price, and at the next step, the retailer makes the decision for the retail price and order quantity. So manufacturer dispatches the order quantity to retailer, and retailer can sell the minimum of the demand and order quantity to the market, or the leftover can be salvaged or discarded as Q minus D plus. And please, you can stop me whenever you want and ask questions. So the things that we assumed in this model is that our model discusses a bilevel optimization, as I mentioned, for several periods. The decision variables are then the prices, wholesale price and retail price, and order quantities for each period. The demand that we have is uncertain and dynamic. Usually depends on retail price, but we want to think a little bit out of the box and think about the influence of previous prices also on the current price. All parameters that we are using are dynamic, and we want to check the time that the distribution of demand is unknown. So it is either because it's expensive, it's costly to find a distribution, or it's not available, we cannot find it. And the only information that we have is the mean and the standard deviation. Both are functions of prices. So what we want to do is to maximize players' payoffs in a distributional robust framework under a Stackelberg game. First, let's look at the what actually is the fundamental or the structure, the general structure of a distributional robust. Let me just move this. Okay, we have manufacturer and retailer. Let's look at the retailer problem, which gets the most influence from the distributional robust problem. In the retailer problem, we have sale revenue plus salvage revenue minus cost. Now I want to see the expectation of this to solve, to optimize our problem. To take the expectation, I have no problem with what I have unless reaching this point, the expectation of D minus Q plus. If I have the distribution of the demand, then it's easily can be found for like what expectation of D minus Q plus is. And in general, for this line, consider that I say that the expectation of the retailer's profit, I've taken this as capital letter pi. Let's do it step by step. For D minus Q plus that we have here, we know that from mathematics, D minus Q plus is 1/2 of absolute value of D minus Q plus D minus Q. So if we take the expectation of D minus Q equals to 1/2 expectation of absolute value of D minus Q plus the expectation of demand minus the expectation of Q. Can you see my arrow?
Yes, we can.
Yes.
Okay. That's good. Based on the Cauchy-Schwarz inequality, then we can say that, because if you look at this equation, we know what expectation of demand is. It is mu, and the expectation of Q is Q. But we don't know the expectation of the absolute value of D minus Q. So from Cauchy-Schwarz inequality, we have the expectation of D minus Q is lower than this bound, the square root of Q minus mu square plus sigma square, right? So I can say that the expectation of D minus Q plus here is less or equal than 1/2. What's the equivalent of this? This is square root plus expectation of D, which is mu, minus expectation of Q, which is Q. So I can write it like this, right? And we say that based on this, so the distributional robust expected profit for the retailer is a lower bound for the expected value of the retailer's profit with known distribution. For the manufacturer, on the other hand, we don't see any changes, like considering the original form for the manufacturer, which is the wholesaler price minus the cost multiplied by order quantity. And just to follow the consistency, I call this expectation the capital letter pi as well, just like the capital letter that we have here. This was the main structure that we have for distributional robust. But now let's talk about the periodic contract, and later we will look at the single contract. In a periodic contract that we have here, we assume that, okay, we know that the demand is mu plus sigma epsilon. But we said that our demand, the demand that we are using, is a function, or can be a function, of all retail prices, historical prices, I mean. So I can write it as phi as a scaling factor, or like memory of the market, which is carrying the influence of all of the previous prices multiplied by small d, which is the demand, the scaled demand. When this phi is 1, phi 1 is 1, it means that at the first period, there is no history, so it is obviously 1. And for any other phi, I can write it as a multiplication of G when G is the memory or the scaling factor at each period. So I can multiply each period in the other period, and like it's a cumulative multiplication to figure the scaling factor at the current period. And this tilde here shows that this small demand is only a function of the current price, when the capital D means demand is a function of all previous prices and current price. So the payoffs for the, here X means the manufacturer and retailer both. The capital J at each period K for the both manufacturer and retailer can be formed as the current value, or the current profit discounted, plus the discounted value that we can get tomorrow, from tomorrow to the future. So this alpha here is the cumulative discount factor when the discount at the first period is 1, obviously. So looking at this, we can see that we have alpha k here and we have alpha k plus 1 here. What's the difference between these two based on this line? It is alpha k multiplied by beta k plus 1. So I can factorize alpha k out here. And I have 1 phi k inside this pi coming from this demand, and 1 phi k here inside this j. I take that one out as well. So I left with alpha k, phi k, jk for manufacturer and retailer. But what is this jk then? The small jk is the scaled pi for the current period plus beta gk plus 1 j. And as we said, when we take this phi k out of this big J, we're left with only current G, this G. So the problem that we have is a bilevel optimization when we solve first the leader problem, the manufacturer, maximization of manufacturer problem, subject to the maximization of retailer problem. But how? It happens in a subgame perfect structure, such that we start from the last period, assuming the last period is n, and solve our problem, figure the variables, the decision variables that we have at that period, and then step back, figure or optimize our problem at that period, and continue this way to reach the first period. As we said, the retailer's profit in a distributional robust structure is a weak lower bound for any case with known distribution. All parameters may be dynamic, and I want to mention once more that the demand is price history dependent. In the literature, we have that in a single period news vendor problem, a fully equipped demand creates more expected profit for the retailer compared to the distributional robust model. As we can see here, pi r is the profit, and we are talking here only about the retailer. The retailer profit at the distributional robust is lower bound for the profit in the model with non-distribution. And we have another thing, is saying that the decision, this QR is the decision of the distributional robust model. The decision that we got from the distributional robust model is not or may not be the optimal for the model with the distribution. And it's obvious from here that if we solve the problem with non-distribution and we get this decision as QD, it is at least better than when we solve or we calculate indeed our model with distribution, with non-distribution, but using the decision variables coming from the distributional robust model. Now we say that we have the same structure in a multi-level or multi-period problem as well. In a multi-period price history dependent supply chain problem, we can have the same relation for the payoffs. So we can say that the payoff of the model with distributional robust is a lower bound for the model with non-distribution, and the decisions coming from the distributional robust model is not optimal for the model with non-distribution. Another thing that we can say here is that, okay, we solved this profit for retailer. We solved this as a distributional robust retailer problem. And we say that for given pair of retail price and wholesale price, the retailer's scaled return is maximized by choosing this order quantity. How? We solved we found the derivative of pi k with respect to q and solve it, and we get q equals to mu plus sigma lambda when lambda is eta minus 1/2 over a square root of eta 1 minus eta, and eta is r minus w over r minus s. This is the optimal q indeed. Now we want to talk about a single contract. Okay, what a single contract is. I want to say that it is a recall. We want to see what we were working on in the periodic contract. We have the same structure for a single contract, as well as the model discusses bilevel optimization for several periods. The decision variables are prices, wholesale and retail price, and order quantities. The demand is uncertain and dynamic and depends on retail prices as a function of all historical prices. And as we said, the distribution of demand is unknown, and the only information that we have is the mean and standard deviation, which are dynamic functions of prices. All parameters are dynamic, and what we want to do is maximization players payoffs in a distributional robust framework in the Stackelberg game. Okay, so what's the difference between a single contract and a periodic contract? In a periodic contract, I said that we start from the last period n, or okay, you know that for instance, when we are at the last period, there is no tomorrow. So the only value that we have looking forward is only the profit at period n. Maximizing pi n can provide us the prices and quantity. Then we go back one step below and find the optimal points and continue this way to reach the first period. So at each period, indeed, we have this structure, which is the current profit plus the discounted, unscaled, or here a scaled value from tomorrow to the future. For the manufacturer and retailer, both of them here, it holds. But in a single contract, on the other hand, we solve actually the problem at the first period, looking ahead. So it is the maximization of the summation of all discounted profits. And this way, it is indeed like we have the whole problem looking at all of the W's, R's, and Q's, decision variables, vectorized form. And we can make the decision simultaneously, such that if, for instance, one player is optimizing his problem and make the decision for one W, he can look at all of the other W, R, and Qs and see if it has it can provide better impact. The player can change the decision. So, why we want to use a single contract? Why we thought to find something like this to present a model that can deal with corrective actions. And to have some examples, we proposed corrective actions exemplified by capacity constraint and pollution tax. In a capacity constraint, we have a maximum allowance, and we cannot exceed or we cannot cross this line. Okay, we have always to be on this line or lower this line. A tax solution, on the other hand, is a unit tax that the players have to pay for each unit of production or pollution generated. This tax is a decision variable for the government, can be paid by both manufacturer and retailer, or manufacturer or retailer, and the model can incorporate any type of price history. So it can be short term, like it is only for 2 periods prices that we are talking about, or a long term, like we are talking about, for instance, from the beginning of the season or beginning of the market so far. For the emission capacity constraint, I want to build a structure. It is like, for the retailer, I have what I had in periodic contract as well, plus a corrective action function. So for the retailer, taking the expectation, I get what I had plus this corrective part. For the manufacturer also, it is equal to what I had plus the corrective actions that I added. And our problem is the maximization of the manufacturer value at the first period, subject to the maximization of retailer profit, retailer value indeed at the first period. And as you see here, the W, R, and Q all are vectorized. And it is very important. It is the only things that we are writing these equations for, that we have to consider that the order quantity cannot be higher than the capacity constraint, if we call this QC as the capacity. In the emission corrective tax, okay, we have 2 players here. Either the manufacturer collects tax or retailer collects tax. For the manufacturer, we have, we were talking in previous slide, if we just go back here, we were looking at this, okay, we have this that we usually have in all of the profit functions for manufacturer, plus a corrective action here. And we have what we had here, and we say that, okay, we know that it should be, or it has to be equal to the to this equation, when we know that the tax is indeed a cost for the manufacturers. So we can write it as this as well. By making them equal and solve it, we can see that, okay, this tau is minus B over Q and is a function of order quantity. For the retailer also, the tax, tau is a tax cost, is a cost for the retailer that has to be collected and sent to the government, for instance. Here also we have this form that in a single contract, we maximize our problem at the first period for manufacturer, subject to the maximization of the retailer at the first period. And as I mentioned, J1 means the cumulative or the addition of all profits at each period when W, R, and Q all are vectors. For this one, we also wanted to figure the optimal order quantity, and to do so, we solved the problem for the retailer with respect to Q, and we get this one. If this BQ is 0, when for the time that we don't have this B, if this B is 0, then we easily can get the same Q as before as mu plus sigma half lambda. And eta here is R minus W also over R minus S. But if this B is something else, is a function of Q, it is a bit more complicated. And if we cannot solve it, that we couldn't solve it in our problem here in this paper, we just prefer to keep it as it is. Okay, what we found here is that the manufacturer gains at least a payoff equal to the subgame perfect total payoff. It means that the single contract can bring more profit, more value for the manufacturer than the periodic contract. A single contract model benefits from taking into consideration all decisions at the same time, and the subgame and the reason is the subgame perfectness restricts the choice of decisions indeed. The decision space for a single contract covers the subgame perfect choices. So we have two things here, that in a periodic contract, we are subgame perfect, we are sustainable results, but in a single contract, we have higher profit, higher values for the manufacturer at least. Because at least for in this paper, we couldn't see any instances that the retailer may get lower by using a single contract. As I said, I also checked a single contract for cap and trade system with a buyback contract. I also use a single contract model here. The model can incorporate any type of price history, long or short term. Here, because of the form that we have for buyback contract, the manufacturer formulation is a stochastic. And okay, by a single contract, by a buyback contract, the retailer shares a part of risk with the manufacturer. The model allows for time-dependent inputs, and the retailer decides on the order quantity considering the buyback price. So we have like retailer price and order quantity as decision variables for the retailer, and we have buyback price and wholesale price for the manufacturer as decision variables. The manufacturers are allocated a maximum, okay, in a cap and trade system, it is like the manufacturer are allocated a maximum allowance of free production. So if he finds the optimal order quantity lower than that, okay, so he has a quota, surplus quota that he can sell to the market or to the other manufacturers. But if he finds his optimal value over this line, he can buy them from the other manufacturers or from the market. So it's like he can trade it. Because of that, we say that cap and trade. And he can make money out of this as well, specifically based on the price of this trading. Okay. And then in cap and trade system, we can say that we have a demand, which is a function of all prices. But here we can write this general form, more general form, when we don't say that it is phi d. It is like we can take the memory out of D and say that this is a multiplication between the scaling factor and the demand. We can write it in a more general form, that it can be incorporated, the price history can be incorporated in the mean and standard deviation in any form. When this R stands for all of the previous prices, but I'm not saying that exactly starting from the first. I can be anywhere at time. So for the manufacturer, I have the revenue that we had minus the buyback cost, minus the allowance buying cost if he wants to buy, plus the allowance selling revenue. So it means that, okay, we know that either this one is 0 or this one. Only one can stay. We take the expectation and we figure that here for the manufacturer now with buyback, we get exactly the same expectation of D minus Q plus that we got in the retailer problem when we were talking about the distributional robust and Cauchy-Schwarz inequality. For the retailer also, we have the sale revenue plus the leftovers revenue when this is B is buyback and S is the salvage value minus the cost of ordering minus the any other cost, operational cost, for instance. Taking the expectation, we get like this equation, simple equation, that we also have this expectation of D minus Q plus. So we also maximize the manufacturer's problem at first period, subject to retailer problem at first period. And looking at these two, we can see that now both can make a different equations that I will show you in next proposition. Okay. We talked about that, okay, the bilevel optimization for distributional robust problem was the maximization of manufacturer subject to the maximization of retailer's problem. When we know that J1 is the summation of all discounted profits. But we know that we have to think that the retail price has to be greater than the buyback plus the salvage, otherwise it doesn't make sense. We talked about what pi m and what the expectation of pi m are. But looking at this expectation of D minus Q plus using the Cauchy-Schwarz inequality that we talked about in distributional robust, we get this equation, which is saying that the manufacturer profit turns to be a lower bound in distributional robust, turns to be a lower bound for the problem with non-distribution. What we get in retailer problem as well. Hence, here we say that for both players, not only one of them, for both players, a value that we can gain in distributional robust is a lower bound for the problem with non-distribution. We get a Q optimal here as well as the if we fix the W, R, and B at period K, the optimal order quantity is when Q is mu plus sigma lambda, when lambda is 2 eta minus 1 over 2 square root of eta 1 minus eta, and eta is now R minus W minus C over R minus S minus B. And you can see that it's obviously that R cannot be equal to S minus B. And because of the economic feasibility, it has to be greater than B plus S. Otherwise, okay, retailer prefer to send back and salvage anything and say that, okay, everything is left over. But we say that the retailer profit is strictly concave in Q for any feasible set of retail and W prices. The unique non-negative solution for this derivative is the global maximum given by this equation. And why we can say that? Why we can say that it is this Q is the global maximum? Based on this equation that we have from mathematics, that the maximization of a summation is less or equal than the maximization of each part. And why it holds with equality? It is because the Q's are independent from each other. So it holds with equality. And we can say that taking the derivative of this Q with respect to B shows that the order quantity is increasing in buyback prices, as we can see that the numerator and denominator are always positive based on the assumption that we have. Okay, what we found is in theoretical findings in a multi-periodic price history dependent supply channel framework, we found that even for the multi-period problem, the distributional robust value or payoff is a lower bound for the model with known distribution. We also found that the decision coming from the distributional robust model is not optimal for the model with known distribution, as this JD is the model with the distribution, but we have calculated with the decision coming from the distributional robust. As we said, the proposed algorithm for the periodic problem is subgame perfect. The optimal order quantity also is a function of prices, as we saw, since we have this phi in D in the demand, which enters in the Q finally, makes it as a function of all previous prices and current price. In a single contract problem, the manufacturer gains at least a payoff equal to the subgame perfect total payoff. For the retailer, we didn't see any instances to show that the retailer may gain less. The single contract underscores the interconnectedness of decisions across different periods. So it might be one reason that the single contract can find the points that the periodic contract cannot go and find those points. A single contract allows for a better utilization for a strategic potential. So the optimal order quantity is increasing in buyback price. And in cap and trade system, the distributional robust approach defines a tight lower bound on both players' expected profits. And it is actually not only because of the cap and trade system, it is coming from the buyback contracts. And for the practical findings, in a periodic contract, the manufacturer cost strongly affects the overall payoff, while the salvage value has a relatively minor influence on payoffs. In a single contract with corrective actions, the capacity constraints may lead to a lower order quantity compared to unconstrained solution, even though the specified cap permits a higher volume. I want to make it more clear that for instance, we have a line and we cannot cross that line. And then even we have solved the problem, and we've seen that we have been sometimes over this line and sometimes below this line. But when we have this capacity and we have to be obliged to follow these capacity rules, we may think, okay, one good solution can be just take the line, this line that we have, the maximum line, it can be one solution. Another solution might be, for the time that we are up, we can accept this line. And for the time that we are lower, we just continue with this lower. But we see that in single contract, the model sometimes even goes lower than that lower line, even though we don't need to make it like to lower our decisions, but for the strategic decisions, the model can find some points to manipulate the other periods, to manipulate the market and gain more. As we checked that this is the optimal problem, is the best among all of the options. Each player achieves higher profits when individually responsible to deal with the pollution tax, even though it's not a big difference. And in a cap and trade system, the viability of a generous buyback price can hinge on the probability of leftover inventory. So it is the time we can say that the manufacturer becomes generous for buyback price when he knows that there won't be that much buyback first, And on the other hand, he's going to increase his prices. So he is manipulating the retailer that I'm offering you a buyback, but with the higher prices. But on the other hand, he knows that the demand of the market, the order quantity, and he knows that he won't get that much leftover. In a cap and trade system, the manufacturer may increase his profits by allowance trading, but the retailer consistently faces a disadvantageous position. Thank you, and I'm ready to answer your questions.